Yeah, okay, so let's start. So, what? This is the seventh problem-solving session, and today we'll first solve problems from week seven's assignment and related problems, and then we'll move on to some questions related to week eight's content in the last few, like let's say last half an hour. Okay, so let's start. If you know the answers to the question and want to answer, you can answer in the chat. Okay, yeah, so let's start. The first question is. Choose the correct options. If an encryption scheme is an authenticated encryption scheme, then it is also CPA secure. Option B is if an encryption scheme is CPA secure, then it is also an authenticated encryption scheme. Option C is an authenticated encryption scheme cannot be constructed using a malleable encryption scheme. And option D is an authenticated encryption scheme is necessarily CPA secure. So which of these options are correct? Yeah, you are right. A and D are correct. So let's go over these one by one and see why. So A is if an encryption scheme is an authenticated encryption scheme, then it is also CPA secure. So recall that a scheme is authenticated encryption scheme if number one, it is CCA secure, and number two, it has ciphertext unforgeability, right? Now, if a scheme is CCA secure, then it's also CCA secure. Sorry, if a scheme is CCA secure, then it's also CPA secure. So an authenticated encryption scheme has to be CPA secure. So A is correct. Option B is if an encryption scheme is CPA secure, then it is also an authenticated encryption scheme. Uh, th- this this is not necessarily true because like there exist encryption schemes which are CPA secure but not CCA secure. And if an encryption scheme is not CCA secure, then it cannot be authenticated encryption scheme, right? So B is not true. Option C is an authenticated encryption scheme cannot be constructed using a malleable encryption scheme. So recall that a malleable encryption scheme is a scheme in which you can, like, given a ciphertext, you can like modify it and get a new ciphertext, right? So basically, you can play around with ciphertext to do things. The adversary can play around with ciphertext to do some things. And option C is that you cannot construct an authenticated encryption scheme using such a scheme. Now this is false because a CPS scheme can be malleable, right? However, we saw in class that if we use, we can construct an authenticated encryption scheme using a CPA secure scheme and let's say SCMA secure MAC, right? By combining these two appropriately, we can construct an authenticated encryption scheme. Oh, yeah. So a malleable encryption scheme is something in which you can, let's say you are given a ciphertext and you can from that ciphertext obtain another ciphertext like which is uh, which is a valid ciphertext. So another ciphertext it would also decrypt to a valid message. Is this fine? Okay, yeah, yeah. So now CPS secure schemes can be malleable, but we saw that by combining CPS secure schemes with SCMA appropriately, we can construct authenticated encryption schemes. So C is not correct. And option D is an authenticated encryption scheme is necessarily CCA secure. This is true because uh, by the definition of an authenticated encryption scheme, a scheme is authenticated encryption if and only if it is CCA secure and also has ciphertext unforgeability, right? So D is also correct. Yeah, so A and D are correct. Now let's look at the second question. The second question is select the incorrect options. Option A is to break the security of a cryptographic construction that is provably secure in the ROM, that is random oracle model. We must discover a weakness of the actual hash function. Option B is there does not exist any ROM based primitive that is efficient and highly secure. Option C is in the ROM model, Unique queries are always answered with unique answers. And option D is there are schemes that are secure in the ROM in, in the ROM but insecure when using any real world hash function. So which of these options are incorrect? Okay, so let's go over this option by option. So the option A is to break the security of a cryptographic construction that is provably secure in the ROM, we must discover a weakness of the actual hash function. Well, this is true, right? Because what is the difference between ROM and the real world? The only difference is we replace a random oracle by an actual hash function, right? Now, if we prove that the scheme is secure when we use the random oracle, the only way it cannot be secure, or that it can be insecure when we implement it in the real world is if there is some problem with our implement with our actual hash function, right? So option A is correct. What about option B? There does not exist any ROM-based primitive that is efficient and highly secure. This was discussed in the class. Like there are some primitives, like there are some schemes which or constructions whose which are in practice fast and efficient, but we can only prove their security in the ROM. So B is not true. Option C is in the ROM, unique queries are always answered by with unique answers. This would have been true if a random oracle were a random permutation, right? However, a random oracle is actually a random function. So it is completely possible that uh, two different, uh, let's say for two different queries, x and x prime, the random oracle answers with the same string y. Because what does a random oracle do? It given a string x, it first checks if it was already queried for x. If it was, it returns whatever it returned last time. Otherwise, it picks a string uniformly at random, right? So for any pair of strings, there is a non-zero probability that the random oracle would answer with the same string. Sure, this probability can be negligible, but it's still non-zero. So yeah, option C is incorrect. In the random oracle model, unique queries maybe it is possible for unique queries to have the same answers. And option D is there are schemes that are secure in the ROM, but insecure when using any real-world hash function. Now, I don't know whether this was covered in the lectures or not, but there are some very contrived and artificial constructions or schemes whose security can be proved in the ROM, but in the real world they are insecure no matter what hash function you use. So there exists some constructions like these, but yeah, these are contrived. So option D is also correct. Is this fine? Okay, then let's move on to problem 3. Uh, let pi equals let pi equals to gen and that be a symmetric key encryption scheme with message space cryptem. Now, what we are going to do is we're going to construct a new scheme pi prime as follows. So we construct a new symmetric key encryption scheme pi prime equals to gen prime n prime det prime for message space m square, that is m cross m, as follows. Gen prime outputs k equals to k0 comma k1 by invoking two independent instances of the gen algorithm to obtain k0 and k1. Then for m0 and m1 in the message space, to encrypt the message m0 m1. Oh wait, yeah, this should be prime over here. To encrypt the message m0 m1 using the key k, we output c1, c0, and c1, where c0 is the encryption of m0 with respect to key k0, and c1 is the encryption of m1 with respect to key k1. Okay, and similarly, to decrypt a ciphertext c0, c1 with key k, we output a decryption of C0 key K0 and decryption of C1 with key K1. And the options are pi prime provides ciphertext integrity. Option B is if pi is multi-message CUA secure, then pi prime is also multi-message CUA secure. Option C is pi is CCA secure, implies pi prime is CCA secure. And option D is pi is CPA secure, implies pi prime is CPA secure. So which of these are correct? Okay, yeah. So okay, the correct options are B and D, and let's see why. So first, let's show that A is incorrect. So consider an adversary A prime or pi prime that queries the encryption oracle or let's say the first message is M0 is not equals to M10 and M01 is not equals to M1. Okay, and suppose that it gets C0 equals to C00, C01, and C1 equals to C10, C11, and C, then, then C defined as C00, C11 is a valid forgery. M defined as M00 and M11. Why? Because C00 is the encryption of M00 with respect to key K0 and C11 is the encryption of M11 with respect to key K1, right? So C is a valid ciphertext for M and adversary A can easily output C, right? So A prime outputs C. So A prime is a PPT adversary that can forge a ciphertext. So I prime cannot have ciphertext integrity. Okay. So A is incorrect. Now let's look at why C is not true, and then we'll see why B and D are true. Okay, so over here we want to show that even though pi might be CCA secure, pi prime might not need not be CCA secure. So what do I have enough space over here? Okay, yeah, we can. So what we'll do is we'll create an adversary that succeeds in the private key CC experiment. Okay, so we have a verifier and adversary, and it. So in this experiment, we can engage in a pre-challenge training phase, but the adversary doesn't do that. What the adversary does is it sends two messages and zero just as before, and M1 equals to M oh, M10 M11, where M00 is not equals to M01. Yeah, oh wait, no, M00 is not equals to M10, and M01 it's not equals to. What would the verifier do? It would pick a weight uniformly at random, and then it would send. Yeah, it would then pick a key unit. It would generate the key or gen prime, and then it would send C is equal to mm, okay, and let's say C is equal to C1 comma C2. And now the adversary can engage in a post-challenge training phase, right? So now what the adversary would do is it would send this ciphertext C prime defined as C0 prime C1, where C0 is anything that's not C1. Sorry. Okay, yeah, let me call this C0 C1. So the ciphertext that the adversary sends is C0 prime C1, where C0 prime is not equals to C0. And now what would the verifier do? The verifier would send M prime. Let me call it, okay, M prime equals to decryption. Okay, let's say M prime is M1 prime, M2 prime. Now what A prime does is the following. It checks is, okay, yeah, let me call this M0. Is M1 the same as M01? If yes, it sets B prime to 0. If no, it sets B prime to 1 and sends B prime to the verifier. So this is what the adversary A will do. Now clearly A is PPT. So now let's look at its success probability. Okay. So first of all, let's see what M prime is. So M prime is the decryption of C prime, which is the same as uh, decryption of Kz with respect to K0 as C0 prime, and decryption with respect to K1 of C1, right? And okay, I don't care what the first thing is. Okay, yeah, let me write it like this. However, uh, so now C1 was a part of the ciphertext that the challenger the verifier sent during the challenge phase, right? So in particular, this is MB1, right? And now we can easily analyze this probability. So what's the probability that B prime is 0 when B is 0? Well, when B is 0, uh, yeah. So when B is 0, okay, yeah, I should write M1 over here first. Yeah, so M1 prime. Yeah, so M1 prime is MB1. So when B is 0, M1 prime is M01. So this check passes. And so B prime is set to 0. So this probability is 1. The other hand, what is this probability? When B is 1, M prime 1 is going to be M11. But since M11 and M01 are different, this check won't pass. And so B prime would be set to 1. And so this probability is 0. Therefore, the difference, this is equal to 1, which is non-negligible. Correct. And so pi prime would not be CCS. Pi prime is not CCS. So yeah, that shows that options A and C are incorrect. And now we are left with proving that options B and D are correct. So what I'll do is I'll just prove that option D is correct. And the argument for option C is, argument for option B is similar. So that you can work it out on your own. So I'll just show you why option D is correct. And uh, so the proof over here would involve a hybrid argument. So yeah, let me first tell you what the hybrids would be. So in the mm, adversary sends M0 equals to M00 and M1 equals to M10, M11 to the verifier in the challenge phase. To prove that the scheme pipeline is CPA secure, we need to show that any PPT adversary A prime, sorry, any PPT adversary A will only be able to distinguish between the situation where M0 is encrypted and M1 is encrypted. So this situation between C is equal to encryption of M0 and with negligible probability, right? Okay, so now I'll define the three hybrids that we would use. The first hybrid is H00, and this is C is equal to encryption with respect to K of M0, and this is this tuple encryption with respect to K0 of M00 and encryption with respect to K1 of M01. Uh, this is the, oh wait, no, let me first define H11. So this was the first view over here. Now, so this view is the same as this view. Now I'll define something similar to this view. So C is, okay. Now we'll define the third hybrid, which would use to show that these two are indistinguishable. And the third hybrid is the following. That yeah, it's directly right. C is encryption with respect to K0 of M00, but encryption with respect to K1 of M11. So are the three hybrids clear? Okay. So now what we'll do is we'll first show that, or rather, yeah, let me just write it. Yeah, no, that was fine. Between H00 and H01 with negligible probability. So first we'll prove that H00 and H01 are computationally indistinguishable. And then we'll show that these two are indistinguishable. That would imply that these two are indistinguishable by an hybrid argument. Okay, so is this fine? So let's prove this. Yeah, so we have a, I don't think I have enough space on this page. So yeah, let me move this entirely to the next page. Okay, so we'll do this using a reduction. So over here we would play the game And so, and between A and A prime, we would have these two views. So let me show you the pre-challenge training phase. So in the pre-challenge training phase, A prime can send messages like, wait, I've been using M1. Okay, so yeah, let me use M1 prime. So, okay, even before this. So at the very beginning, what we would do is it would pick a key, K0 using, okay, wait, we are distinguishing between H00 and H101. Okay, yeah, so this should be K1. And A would pick K0 from, so initially both A and V pick two independent keys. Then when A prime in his pre-challenge phase sends messages M prime 1 to M prime S to A. Okay, yeah, let me shift this more. What uh, what A does is the following. It sends M prime 1 1 to M prime S1 to V, and V is going to reply with C prime 1 1 to C prime S1, where C prime I 1 is then A would compute C prime I2 for I0, which is the encryption with respect to K0 of M prime I 0. Construct this and send this C prime 1 to C prime S to A prime. So this is the pre-challenge training phase. So what's happening is over here, A is acting as a middleman, and it's A who is playing with key K0 and V is playing with key K1. Okay, now, oh yeah, okay, yeah. So A prime is a middleman and A is our original adversary. Yeah, I messed the notation up. Okay, so now A prime would in its challenge phase send two messages, right? So it sends M0 is equal to M00 comma M01, M1 equals to M. And what A prime does is it's going to just forward M01 and M11 to the verifier. The verifier would pick a bit be uniformly at random from 0, comma 1, compute CB equals to, CB to A prime, and A prime will what A prime will do is it's going to compute. Okay, it's going to first. Yeah, let me just write it down. It's going to. Okay, let me call this CB1. It's going to compute CB0, which is encryption with respect to K1 of. Okay, what are we distinguishing between? H00 and H01. So it's going to. Uh, yeah, and it will at CB. Okay, why am I writing B over here? I just write C0, C1. And it will send C to A prime. Then there is going to be a post-challenge training phase. But this is similar to the pre-challenge training phase, so I'm not writing it. Okay, and now, yeah, A would send B prime. Now okay, so over here, if A, over here both A and A prime are PPT. So now let's look at what the view of A is. Okay, so yeah, when B is equal to 0. So when B equals to 0, what is C zeros? Oh, I should write C1 over here. So when B is equal to 0, C1 is the encryption of M01. Okay, let me write it. So C equals to, they want here, right. Yeah, so C is going to be the encryption, and let me see, is this, wait, no, 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 I wrote it the other way around. Keys were wrong. So C is the encryption of K0, M00, and K1 of M01. And what are the views? Wait, wait, something wrong. So this is M0, okay, and M00. Okay, yeah, so when C is 0, the view is this, right? At 00, encryption of M00 with respect to K0 and M01 with respect to K1. So the view is similarly when P is equal to 1, C1 is going to be encryption with respect to K1 of M11. So when B is 1, its C1 is encryption of K1 respect to M11 over here. And so C will be encryption with respect to K0. So this doesn't change, right? C0 is always encryption with round key. So C0 is always the encryption of M00 with respect to key K0. This doesn't change. Okay, so it's M00 with respect to K0 and M11 with respect to K1. So let's see what that was. That is this, right? M00 with respect to K0 and M11 with respect to K1. So so A prime's view is, sorry, so A's view is mm, H, what was they calling it? 01. Yeah, 01. Okay, I think I don't need this. Now, if uh, A can distinguish between H00 and H01 with non-negligible probability, then okay, so let's see what H00 and H01 correspond to for A prime. So when A's view is H00, A prime's view is B equals to 0, right? In the this game, private key CCA A comma pi. And when A's view is H01, A prime's view is B equals to 1, right? So if A can distinguish between H00 and H01, A prime can distinguish between mm, sorry, okay, so, okay, let me write it like this. With non-negligible property, right? A contradiction because so A can only distinguish H00 and H01 with negligible probability. And this was exactly the claim, right? So yeah. So now similarly we can prove this claim. So okay, recall that we wanted to show that these two are indistinguishable. We have already shown that these two are indistinguishable. As long as we show these two are indistinguishable, by hybrid argument, these two would be indistinguishable, right? So now we want to show that these two are indistinguishable. So our claim, so yeah, the claim is this. It's the same. So let me copy it. Yeah. Okay. And okay, I won't do the entire proof because the proof is similar to claim one. So what I'll do is I'll just copy the game and tell you what the changes are. Can I fit it? Yeah, I can fit it. Okay, so earlier this was K0, now this would be K1. This would be K0. These would be M prime 10 to M prime S0. This would be C prime I0. He would be K0 and it would be M prime I0. And C prime 10 to C prime S0 would be that. So this would be I1 K1 and over here it would be I1. Yeah, C prime I would still be computed accordingly and this would be sent. Now again M0, M1 would remain the same, but now it would send M00 and M01. No wait, it would send M00 and M10. Yeah, two messages. So in the previous case, these two were being sent. Now these two would be sent. This is C0. This is K0. This is B0. This is 0. Now, instead of computing C0, it needs to compute C1. Uh, K1 of, okay, let me see. It's 0010 and what it's 0. Okay, what were the views? So it's M11, M11, MS00. Yeah, so now it's M00, M10, it's going to be M11 over here. Yeah. Okay, so now we can again similarly analyze the view of A, but yeah, let me not do the entire thing. Let me just quickly tell you what the view is going to be. So when B is 0, what does it see? It sees the encryption of, okay, so when B is 0, it sees the encryption of M00 and M11. And when B is 1, it sees the encryption of M10 and M11. If I were to go back to the views, M00, M11 is H01 and M10, M11 is H11, right? So, yeah, when B is equal to 0, A's view is H01. When B is equal to 1, A's view is H11. So again, much just like in the proof of claim 1, if A can distinguish between these two views with non-negligible probability, and A prime can distinguish between C equals to 0 and C equals to 1 with non-negligible probability, which is a contradiction, right? So yeah, the rest of details are the same as yeah. So I'm not working out those details. They are exactly the same as the details in the proof of claim 1. So now what we have shown is that, yeah, oh, wait, I did not correct the claim statement. Yeah, so in this claim, we proved that uh, H11, H11 and H01 are indistinguishable. Earlier, we had proved that H00 and H01 are indistinguishable. So first we proved this are indistinguishable, then we proved these are indistinguishable. So these two have to be indistinguishable by the hybrid argument, right? And as we argued at the very beginning, if these two are indistinguishable, we are done. Yeah, so this completes the proof of why part D is correct. This was a very long proof, but yeah. So is this fine? And again, the proof that B is correct is similar to this. So I'm not doing it. Okay. Is this fine? Yeah, I'll just wait for a minute if you have a question. Okay, so let's move on to the fourth problem. The problem is choose the correct combination. Yeah, choose the correct combination for a commitment scheme. Uh, so this is like we are supposed to match the left hand side with the right hand side. The left hand side we have receiver, corrupt sender, honest sender, corrupt receiver, and sender. On the right hand side we have hiding property provides opening information, accepts or rejects the data M, and D is binding property. So can someone tell me what should match to what? Okay, yeah. Okay, that's correct. One should match to C. Yeah. 2D corrupt sender, honest receiver. Yes, corrupt sender, honest receiver is D. What about 3? Okay, so 3 maps to A, and finally 4 maps to B. Okay, so yeah, let's see that. Okay, so uh, okay, so what does okay in a commitment scheme, what does the sender do? The sender commits to some value, right, and sends that value to the receiver, and that's the commit phase of the commitment scheme. In the open phase of the commitment scheme, the sender would send the opening information of the commitment to the receiver, right? And the receiver would check if it can open the commitment using that uh, opening information. And if it can, then it would open it and accept the data M, right? So the receiver is go so receiver is so just this part tells us that receiver is going to accept or reject the data, and that sender is going to provide the opening information. So we are done with these two. Now we have to look at these two, right? Now, okay. Suppose you have a corrupt sender and an honest receiver. Now, what would a corrupt sender want to do? A corrupt sender would want to do the following. It would want to commit to a value m, but then open it to some other value m time. Okay. So, okay? So, what is going to prevent a corrupt sender from doing this? It's the binding property of the commitment, right? Because what does the binding property of the commitment say? The binding property of the commitment says that once you have committed to a value, the sender cannot find another value m prime to open the commitment to it, right? So 2 maps to D. And what about 3? Okay, now we have honest sender and corrupt receiver. Now, what would a corrupt receiver want to do? The corrupt receiver would want to do the following. The moment it gets the commitment, even before the commit phase, the moment it gets the commitment in the commit phase, it would want to know what value is committed even before the sender sends him the opening information, right? So the honest, so if the sender is honest and the corrupt receiver is correct, the receiver would want to open the commitment on its own. But what is preventing the receiver from doing that? It's the hiding property. We call that the hiding property said that without the opening information, it's very difficult to open the commitment and find out what has been committed. Okay, so 3 maps to A. Is this fine? Yeah. So if this is fine, let's move on to the next problem. Okay, so the next problem is as follows. Let E k comma n and D k comma c for any key k chosen at random be a crypto system that provides an authenticated encryption. Consider the following crypto systems and choose the correct option. The first crypto system is defined as follows. Its encryption algorithm is E1, and to encrypt a message M using key k, it just outputs C comma C, where C is E of k comma M. And to decrypt the ciphertext C1 comma C2 using key k, it just outputs D of k comma C1. And the second scheme is almost the same. To encrypt M using key k, it outputs C comma C, where C is as before E k comma M. And D2 is to decrypt a ciphertext C1 comma C2. D2 outputs D k comma C1, but only if C1 and C2 are the same, And if C1 and C2 are not the same, then it outputs this symbol, which is the symbol for failure or incorrect ciphertext, right? So these are the two schemes. The only difference between the two schemes is this. In the second scheme, we check if C1 and C2 are the same. In first scheme, we don't do that. So the options are only the first scheme provides CPS security and is it also has ciphertext integrity. Option B is only scheme 2 provides CPS security and has ciphertext integrity. Option C is both provide CPS security but not ciphertext integrity. Option D is both provide ciphertext integrity but not CPS security. And option E is both provide CPS security and ciphertext integrity. So which of these options is correct? Okay, yeah. So the correct answer is B. Only two provide CPS security and ciphertext integrity. Let's see why. So the encryption scheme of both 1 and 2 is the same. So what I'll first prove is that that scheme is CPS secure. Okay, let me add a new page. So first we'll show that okay, yeah. So again, we'll do this by reduction. We'll show that if you can break either one or two, you can break the original scheme E comma D. You have V, you have A, and you have A prime. And so this is a CPS security game. So over here, A prime is going to be the challenger for or adversary for either E1 or the first scheme 1 or scheme 2. It doesn't matter. And A is going to be the adversary for the original scheme E comma D. Okay. So since this is a CPS security game, there is going to be a pre-challenge training phase. And let's say in this phase, A prime sends messages M1 to MS. And A is just going to forward these to B. Let me, and what does V do? We picks a key K uniformly at random and sends C1 to CS, where CI is E of K comma Mi. Now, A prime is the adversary for scheme either 1 or 2, so it should get a message from C comma C, right? So what A will do is it will send C prime 1 to C prime S, where C prime I is equal to, yeah, let me not use, yeah, so A will just send this C1 comma C1 to C1 comma CS, sorry, CS comma CS. Now, regardless of whether A prime is the adversary for scheme 1 or scheme 2, this C11, C1 comma C1 to CS comma CS are valid ciphertext for M1 to MS, right? So far it's the view is fine. Then in the challenge phase, let's say A prime sends M0, M1. Again, these would just be forwarded. Then a B would be picked uniformly at random. Let me start. And this is sent back. Oh wait, there is a post-challenge training phase. So the post-challenge training phase is going to be the same as pre-challenge training phase. So I won't write it. Yeah. And then A prime would send B prime to A, and this is going to forward. So first of all, notice that if A prime is an efficient machine, then so is A. And by assumption, A prime is an efficient machine, so A is also an efficient machine. So A is PPT. And what is this difference? So we want to argue that this probability is non-negligible, which would give us a contradiction, right? But since A prime just forwards the B prime it gets from A, this probability is the same as, yeah. And this, by assumption, is non-negligible because we are assuming that A is an adversary for either E1 or E2, or scheme 1 or scheme 2, right? So this proves that both schemes give you CPS security because the original scheme was authenticated encryption scheme, therefore CCS secure and therefore CPS secure, right? So is this fine? Because then we can move on to ciphertext integrity. Yeah, I think in the answer key that you got, I think the option given over there is option C, right? Yeah. Oh, okay. So if this is fine, so this was just showing that both schemes have CPA security. Now let's show that one does not give you ciphertext integrity, but two does. Yeah, first I need to add a new page. Can I write it? Yeah, I can write it in this first place. Okay, so let's see why. Okay, so what's happening in one is the following, right? Yeah, so I think in the assignment the option is C, but I think the answer should be B because we can prove that two does give you ciphertext integrity. So yeah, let me show you the proof then. Yeah. But yeah, let's first see that A does not provide hypertext integrity. Okay, so what do we do in A? We don't, when we want to decrypt something, we don't even look at C2, we just decrypt C1. Okay, now here's the problem. So what an adversary can do is the following. Where is the encryption oracle for any message and obtains C comma C. We are looking at scheme 1, so it's C comma C and outputs C comma C prime, where C prime is not equals to C as a forgery. Now D2, sorry, D1 for scheme of K C comma C prime. So in the scheme 1, we were completely ignoring the second ciphertext, right? Second part of the ciphertext, which in this case is C prime. So this is just T of K comma C, which is going to be the message, right? Because C was, so how is C going to be obtained? C comma C was obtained by invoking E1 on M, and E1 on M is just you obtain C from E1 on M is just uh, the tuple E on M comma E on M, right? So yeah, C does decrypt to M, and this is a valid forgery, right? Yes, this shows that one does not provide ciphertext integrity. Now let's try to show that two does provide ciphertext integrity. First of all, notice that what we did over here, this attack that we gave against one won't work against two because C and C prime are different. And in the second scheme, we are checking if C and C prime are different or not. If they are different, we are saying we are outputting failure, right? Or outputting failure or invalid ciphertext, whatever you want to call this symbol. So yeah, this attack that we showed against one does not work against two. Now let's see why two is ciphertext, does provide ciphertext integrity. So again, we'll do this by a reduction. Over here, we would play this game. So enforce for scheme with adversary A and scheme E comma D. Yeah, N is always there. And here we'll play the game adversary A prime and scheme E2 comma D2. Okay, now what will A2, what can A2 do? It can ask for, it can train itself. So let's say it does this. A is just going to forward these to the verifier. The verifier would pick it the compute Ci is equal to E k comma mi and send these. Now, what is A2 expecting? It is not expecting C1 to CS. It is for the second scheme, right? So it's going to expect C1 comma C1 to CS comma CS. And then it will output a forgery. Now, since this is a valid forgery for the scheme E, E2 comma D2, and in that scheme we are checking if the two parts of the ciphertext are the same, the forgery has to be of the form C star C star, right? And in this case, it will just send C star. Yeah. Okay, so now let's see this. So what is the probability that, so now what we'll show is that if A2 succeeds with large probability, then A must also succeed with large probability. So we want to show that this is large. So what is this? This is the same as uh, this. Okay, I have space. Let me write this below. But okay, now since C star comma C star is a valid forgery for the scheme E2 comma D2, this means that C star. i- Okay, yeah. This means that C star is, okay, but yeah. So if A succeeds with non-negligible probability, then should A. Oh, wait, no. So A2 succeeds with non-negligible probability. Yeah, so if A2 succeeds with non-negligible, I should write A2 here. Yes, if A2 succeeds with non-negligible probability, then so should A. But A cannot succeed with non-negligible probability because the scheme E comma D is has hypertext integrity, right? So therefore A2 should also not succeed. Is this fine? Yeah, and here we crucially use the fact that the two ciphertexts were the same, right? Because yeah, that check is being performed. That's the difference between the two schemes. Is this fine? Okay, so in that case, let's move on to the next problem. Right, it is cool. Okay, okay, so yeah, so the next problem is the following. Consider the following Merkle tree. It has 15 nodes, and Alice stores the entire tree, while Bob has the contents of node 1, just this node 1. Suppose that Alice wants to convince Bob that the data stored in node 11, that is this node, is some particular string x in 0, 1 to tn, right? Then what are all the nodes whose contents should she reveal to Bob apart from node 11? So what all nodes should Alice also send over to Bob so that Bob can verify using this x. So Bob can verify using the first node that it has stored that x is indeed the content of node 11. So is the question clear? Okay, so yeah, uh, let's see which nodes should she reveal. So the answer is 11. So 10, 4, 3. And let's see why. So let Ti denote the content of the ith node. So now Bob can compute. Okay, so what does Bob have? Bob has the content of cell 11, or rather the claim content of cell 11x. He has the content of cell 10, cell 4, and cell 3. Okay. So Bob can compute T, what's the number? D5, the hash of T10. So D5 is going to be the hash of D10 and the content of cell 11. And Alice is claiming that the content of cell 11 is X, or node 11 is X. So Bob can compute this efficiently. So this is the first thing Bob does. Then now Bob has D5. So Bob can compute D2, D4. Why? Because Alice has also given the content of D4 to content of 4 to Bob. So she has given D4 to Bob. Bob just computed D5. So he can easily compute H of D4, D5 efficiently. So Bob can also do this. Now Bob has D2. So Bob can compute D1. Why? Because Bob computed D2. Alice has given him D3. So she can easily compute H D2, D3 efficiently, right? Then what does Bob do? If D1 is equal So recall that Bob already has stored the content of node 1, right? So Bob will compare the content of node 1 that is has just computed D1 is equal to the if they are the same. Bob accepts. Uh, the content of cell 11 is x1, sorry, x. Otherwise, Bob knows that. Why? Because if the content of cell 11 were x, then D1 would exactly be the same as the node that he has stored, because that's how that node was computed. On the other hand, if the content of D11 is not x, but let's say some other content x prime, then the only way D1 can be the same is if D2 is if basically Alice was able to find two different x and x prime so that there is a collision, right? But since H is a collision resistant hash function, this cannot happen. So, or rather, this can only happen with negligible probability. So, with okay, so only with negligible probability would Alice be able to convince Bob of, or rather, would he be able to convince Bob of the wrong contents of cell 11. So once Bob does this with like 1 minus negligible probability, he knows that the content of cell 11 is X. Is this fine? Okay, so if this is fine. Let me see how much time we have. Okay, we just have half an hour, so let's move on to the problems related to the content of week 8. And if we have time, we'll come back to 7 and 8. Now let's solve some problems from week 8. The first problem from week 8 is choose the correct options when the authenticate then encrypt approach is instantiated with a CPA secure scheme and an SCMA secure MAC. Excuse me. So the options are the resulting scheme is CCA secure, but not an authenticated encryption scheme. Option B is it does not provide ciphertext integrity or CI. Option C is it provides ciphertext integrity. And option D is it is not CCA secure. So which of these four are correct? Uh, one and okay, wait, multiple answers. One, two, three. Okay. Okay, so let's go over this option by option. So it is CCA secure, but not an authenticated encryption scheme. I think, yeah, yeah, actually, yeah, I think one is true. We can show that it's, oh, wait, it's not, no, it's not even CCA secure. Yeah, so one is not true. The scheme is not even CCA secure. Yeah, okay, I'll talk about why one is not true when I talk about option B. So option B is, so yeah, option A is incorrect. Option B is it does not provide ciphertext integrity. So this is correct. And why? Okay, so recall that in class we saw that if we use any SCMA secure MAC with CBC mode of encryption, there's something called padding oracle attack, right? Now, if you recall, what we were doing in the padding oracle attack was we were constructing the ciphertext We are basically forging a ciphertext. So now since the CBC scheme is CPA secure and the PRF, when the underlying PRP is secure, what we saw in class gives us an example of a CPA secure scheme and a SCMA secure MAC which do not give a ciphertext integrity because of the pedagogical attack. So B is correct. And okay, so it does not provide ciphertext integrity, so C cannot be correct. And option D is it is not CCA secure. Okay, this is also correct because recall that in the padding oracle attack, we were also finding out the last bit of the last byte of the message, right? Last byte of the last block of the message. Now it turns out that using an attack very similar to the one that we saw in the class, we can in fact not only recover the last byte of the last block, but we can recover in fact the entire last block of the message. And then using that we can, yeah, using that an adversary can use that block to distinguish between whether message M0 was encrypted or whether message M1 was encrypted. So once we figure out the last block, we no longer have CCA security. So both B and D are correct. Is this fine? Yeah. On the other hand, if we so over here we are using authenticate then encrypt. If we had used encrypt then authenticate, then yeah, then we would have CCS, then we would have CCS security and ciphertext integrity both, and so we would have had authenticated encryption scheme. Yeah. So the order in which you do which you do the two operations, encryption and authentication, they matter. Yeah. So if this is fine, we can look at the next question. So the next question is the following. Which of the following is or are sufficient to build an authenticated encryption scheme? The options are a PRF, that is a pseudo-random function. Option B is a PRG or a pseudo-random generator. Option C is a hash function. And option D is all of the above. So which of these are sufficient? Okay, D is not entirely correct. Okay, A and C is also not correct. Okay, let me tell you what the answer is. It's A and B. Okay, so let's first see why A is sufficient. Okay, so we know that using a CPA secure scheme and SCMA secure MAC and the encrypt then authenticate framework, we can construct an authenticated encryption scheme, right? Oh yeah, the hash function is collision resistant. Okay, yeah. So let me write it. Okay, yeah. So where was that? Okay, yeah. So using CPA secure scheme and SCMA secure MAC, we can construct an authenticated encryption scheme. Now recall that if we have a secure PRF, we can construct both and a CPA secure scheme, encryption scheme, as well as an SCMA secure MAC. So from PRF, we can consider an authenticated encryption scheme. Okay, so option A is correct. Now for option B, recall that we saw that from a PRG, you can construct a PRF. If you recall, that was this tree construction. So from a PRG, we can construct a PRF. And from a PRF, we can construct both a CPA secure scheme and an SCMA secure MAC, and therefore an authenticated encryption scheme. So B is also correct. What about C? Well, using C, we can construct secure MACs, but using C, we only know how to construct a secure PRG in the random oracle model, right? So right now we don't know how to use a collision resonant hash function to construct a PRG outside the random oracle model, right? So we can't. So while this option C does give us a MAC, we don't know if we can also get a CPS secure scheme from it, right? So option C is not correct, and so option D is also not correct. Now, if we were working in the random oracle model, then C would also have been correct. Is this fine? Yeah. So okay, at least I don't know of any construction of a PRG using a collision resonant hash function outside the ROM. Like, so the only construction of a PRG using a CRHF we saw in class was assuming that we were in ROM, right? Yeah. So A and B are correct, and in the ROM, all of them are correct. Yeah. So now let's move on to the next problem. So consider a key agreement protocol pi equals to pi s comma pi r. Then after looking at the transcript pi, a PPT adversary cannot compute the key but can figure out this information. So what is this information? The information is the absolute value of the difference between the probability that the first bit of the key is 0 given the transcript minus first bit of the key is 1 given the transcript is at least is one third. Okay. So the adversary cannot find out the key, but it knows some information about the key. That that the key is either more likely to have the first bit 0 or either more likely to have first bit 1. Okay. So now which notions of privacy does the key agreement protocol satisfy? The options are strong privacy, weak privacy, and neither. So which of these are correct? Okay. So first of all, since the PPT adversary cannot compute the key from the transcript, weak privacy is clearly satisfied, right? Because what does weak privacy say? Weak privacy says that given the transcript, no PPT adversary should be able to find out the key with non-negligible probability, right? So weak privacy is already satisfied. What about strong privacy? Well, recall that in strong privacy, what we needed was the following. Uh, by looking at the transcript, the adversary should not be able to distinguish between uh, key and so after looking at the transcript, the adversary should not be able to distinguish between the key and a totally random string, right? Now, in a totally random string, this difference is exactly zero, right? Because the first bit is likely to be 0 or 1, right? However, over here, the adversary is able to get this information. And so using this information, it can distinguish between key and a totally random string, right? So strong privacy is not satisfied. Is this fine? Yes, so if this is fine, we can look at the next problem. So the next problem is consider a key agreement protocol pi equals to pi s comma pi r such that the key computed using pi is a pseudo random string. Which notions of privacy does pi satisfy? So which notion does it satisfy over here? Okay. So turns out over here it satisfies both. The reason is the following. If the key is a pseudo random string, then since any PPT adversary cannot distinguish a pseudo random string from a totally random string, any PPT adversary cannot distinguish the key from a totally random string, right? So the notion of strong privacy is satisfied, and we know that if strong privacy is satisfied, weak privacy is also satisfied. So both A and B are satisfied. Is this fine? Okay, so if this is fine, let's look at the next problem. So the next problem is the following. So it's about groups. So in actually it's about groups. So in like this week we also saw what cyclic groups are. So I think the next three problems are about groups and cyclic groups. Okay. So let G, comma this group operation. So I'll denote the group operation by a dot. It's not multiplication, it's just group operation. So let G, comma a group operation be a group. Then what is the maximum possible number of generators that G can have? Now recall that the generator of the group is any element small g such that every element of capital G can be written as G to the I for some like some natural number I, right? That is, every element of G can be obtained by performing group operation by performing by iteratively performing group operation of G with itself, right? The question is what is the maximum possible number of generators that G can have? So, like, would you like to guess what the answer is? It just follows from the definition. Almost correct. Yeah, its order of G is almost correct. So yeah, the answer is this. So I'm using size of G to denote the order of G. And the reason is the following. So there are two cases. Case one is that size of G is exactly, yeah, except identity. But there is one case. So, okay, it's not always except identity because if it was just except identity, it would have been size of G minus one, right? There's just one corner case we need to handle. That's case one. So what if size of G is one? Then G is thus this, right? Exactly. So when it is trivial, E would be the generator, right? So E is a generator. So when size of G is 1, we get 1. And what about case 2? Okay. So okay, in case 2, everything. Okay, in case 2, there exists G in G minus E, right? E group operation with E is E itself. E to the I cannot be, I should write I in Z. Yeah, and whenever size of G is written equals to 2, size of G minus 1 is going to be at least 1. So yeah, the max of 2 would be size of G minus 1. So in case 2, it's size of G minus 1. Now, yeah, Yeah, you wrote that G is cyclic, right? So when G is cyclic, like, or rather when G is some very particular cyclic group, like let's say ZP star or ZP cross for a prime P, then yeah, so there are some cases in which all the non-identity elements are generators. So there exist groups where size of G minus 1 is also achieved. Is this fine? Okay, so yeah, in that case, let's move on to the next problem. So the next problem is the following. Let Gn be the set of all complex nth roots of unity. Pick the correct options. A is Gn comma plus is a group. Option B is Gn comma product is a group. Option C is Gn comma product is an abelian group. And option D is Gn comma product is a cyclic group. So now, like, okay, do you know what a root of unity is? Or should I recall it? Okay, so a root of unity is any complex number omega such that some power of omega is 1. That is, there exists an I such that omega to the I is 1. And in this case, I is n because we are looking at the nth roots of unity. Okay, yeah, is anything that satisfies x to the n equals 1? Yeah. The question is, like, which of the options are correct? So, like, would you like to take a guess? Okay, C is correct. But if C is correct, then B also has to be correct. What about A and D? Okay, so yeah, turns out D is correct, but A is not. And yeah, so let's see why. So, okay, why is A not correct? Well, 0 is the additive identity. Yeah, okay, I'll explain why D is correct. That requires proof. So, a group must have an additive identity. So, Gn comma plus, since the group operation is plus, it must have an additive identity. Now, over complex numbers, the additive identity is 0, but 0 is not a root of unity. So, 0 is not in Gn, and therefore Gn comma plus cannot be a group. So, that handles case A. Now, what about B? Uh, okay, so if so, we need to so for B we need to show 4 properties. For C we need to show 5 properties. The first property is closure. Let omega 1 comma omega 2 be in Gn, then omega 1 to the n equals to omega 2 to the n equals to 1. So omega 1 omega 2 to the n equals to omega 1 to the n, because over complex numbers multiplication is also associative. So omega 2 to the n, sorry, multiplication is also commutative, which is 1, right? So omega 1 omega 2 is in Gn. So closure is satisfied. The second is associativity. Yeah, and we know that multiplication is associative over complex numbers. So associative is also satisfied. Identity. So now for any omega 1, Omega times 1 is equal to 1 times omega is equal to omega. And also 1 belongs to Gn as 1 to the n is 1, right? So it has identity. So what about inverse? So for any omega in Gn, consider, okay, for any omega 1 in Gn, consider omega 2 defined as 1 over omega 1. Division for complex number is also defined, so I can do this. Okay, so now omega 1, omega 2 is equal to omega 2, omega 1 is equal to 1. Also, omega 2 to the n is equal to 1 over omega 1 to the n is equal to 1 over omega 1 to the n is equal to 1 over 1 equals to, right. So every element also has an inverse in the group. And 5 is, so 1 to 4 prove that B is true. For C, we also need commutativity, but we know commutativity. So we know that is commutative. Okay, so now let's look at D. So here's the fact. So I don't know whether you know this or not, but every root of unity can be written like this. I'm sorry, every nth root of unity can be written like this. Yeah, so now, yeah, yeah, it was taught in GW. Uh, what is this root of unity? So omega is a generator of Gn, right? And so Gn is cyclic. That proves D as well. Yeah, so, oh, right. So, okay, but why do we need a primitive root of unity?
साइक्लिक के लिए नहीं करना पड़ेगा। आपने बोला ना साइक्लिक ग्रुप चाहिए।
Okay,
साइक्लिक
but
ग्रुप के लिए तो मतलब अब nth रूट है तो इसका मतलब है कि nth पावर करके तो आ रहा होगा 1, बट जरूरी थोड़ा ना है कि उसकी सारी सब पावर आ जाएगी, मतलब सब रूट ऑफ यूनिटी आ जाएंगे।
okay, so that is what we showed, right? So Gn, the set of all roots of unity, is e to the I 2 pi over n. Okay. And I goes from 0 to n minus 1. So what I'm doing is I'm picking omega to be e to the 2 pi over n, right? Now what is omega to the I? Omega to the I is e to the 2 pi over n to the I, which is, so omega to the I is this, and this is this, right? So for every I can obtain this as a power of omega, right? That shows that omega is a root of omega is a generator, right? Regardless of whether n is prime or not. So for example, okay, if you want an example, here's one. Let's say n equals to 4. Okay, then Gn is equal to 1 minus 1 I minus I. Yeah, and okay, so I square is minus 1. I cube is I times I square is I times minus 1 equals to I. Uh, I cube is, oh wait, I did already did I cube. And I to the 4 is 1. Or rather, I should have, I to the 4 is 1, right? So I generates minus 1 minus, oh wait, this is minus I. What am I doing? So I generates minus 1 minus I and 1, right? So I is a generator of Gn, but 4 n which is equal to 4 over here is not a prime. Okay. So even in this case, uh, there is a generator. Is this fine? Okay, so if this is fine, it's already 6. So if there are no other questions, so if you have any questions, you can ask me now. But if there are no other questions, we can end the session today. I'll just wait for 1 or 2 minutes. Yeah. Okay, so I don't think there are any questions. So yeah, let's end the meeting. We can meet next Saturday at the same time. Thank you.